In this section, we'll discuss some of the basic features of semiconductor band structures, including the effective mass of electrons and holes. So far, we have discussed two ways to describe electronic wave functions in a crystal. The goal has been to develop the dispersion relation of energy versus wave vector. In both cases, we have used block wave functions to describe the overall wave function of the electron. The block wave function contains two parts. One, which is a periodic function with the periodicity of the lattice, and then the other is simply a wave which describes how this periodic function can change in space. In the case of the free electron, we approximated this periodic function as simply a constant, and so we only had the e to the I kx free electron part of the wave function. This gave us a simple parabolic dispersion relation, which we drew in our energy versus K diagram, and then we recognize that at the Brillouin zone edge, there should be some disruption in the energy. We have also described our wave function as a linear combination of atomic orbitals. In this case, the simple additive combination of the atomic orbitals is our periodic function. Then we use a simple wave to describe the various combination of bonding and antibonding possible between the atoms. For the linear combination of atomic orbitals, we recognized that the absolute value of the wave vector k could be at most pi over a, because this represented the most antibonding combination. And so our band simply ended at plus or minus pi over a. Our free electron bands, on the other hand, continued past the first Brillouin zone. Let's take a closer look. The wave function at k plus 2 pi over a can be written as e to the I kx times e to the I 2 pi over ax. Because e to the I 2 pi over a times x is a periodic function with the same periodicity as the lattice, we can move it over to the side where the periodic function is. We then recognize that this function is simply a periodic function, just like the one we had before, but with an extra twist every cycle. Where our free electron wave used a constant before, now we have a periodic function with one oscillation in between each atom. Because this wave function is also a block wave function, it can be described on the E versus K dispersion relation with wave vector k as opposed to k plus 2 pi over a. This corresponds to being able to move the wave functions in the second Brillouin zone into the first Brillouin zone. Normally, when we draw band diagrams, we shift or fold back all of the wave vectors outside the first Brillouin zone into the first Brillouin zone, and this is known as the reduced Brillouin zone scheme. In the linear combination of atomic orbitals, or tight binding model, we recognize that the absolute value of k needed to be less than pi over a. This gave us a cosine type wave function for an S state. If we do the same for the next higher energy P state, we will also get a cosine function, but of opposite sign, because initially we have antibonding interactions, and as we go to higher wave vector, we will get more bonding or lower energy. For free electron wave functions outside the first Brillouin zone, we recognized we could move them into the first Brillouin zone. While we always do this using the reduced Brillouin zone scheme, we should recognize that this corresponds to wave functions with an extra oscillation within the unit cell. Notice how similar the band structures and wave functions look, regardless of whether we used a linear combination of atomic orbitals or a free electron model. The band structures of real three-dimensional crystals will be somewhat more complicated than the one-dimensional examples shown here, but will have many common features. For example, some bands have their lowest energy at the k equals 0 or gamma point and then run up to a maximum at the Brillouin zone edge. Other bands have a maximum at k equals 0 and then run down. Often this feature alternates as we move higher in energy due to the wave functions switching from symmetric to antisymmetric and then back to symmetric again. In the free electron model, we use the parabolic dispersion relation of energy versus K to understand the physical properties of metals. As the electronic band structures become more complicated due to the interaction of the electrons with the atoms and the atomic orbitals, we can still utilize the parabolic dispersion relation, where we think of the mass as an adjustable parameter or effective mass. If we take the first derivative, dE dk, of our dispersion relation, we get 2 h bar squared k squared over 2m, which is h bar times momentum over m, which we recognize as h bar velocity. This velocity is known as the group velocity of the electron wave and depends on the slope of the E versus K dispersion relation. Then when we take the second derivative of E versus K, we will simply get h bar squared over m. We will use this second derivative of E versus K as the definition of our effective mass, m star. Bands with large or sharp curvature will have a large second derivative and therefore a low effective mass. They will also be associated with a high slope and high group velocity. On the other hand, flat bands with low curvature and low slopes will have large effective masses and small group velocities. Effective mass is also associated with bandwidth and density of states. When we have large atomic orbital overlap, we have a very dispersive band, which translates to it being very wide in energy space, and that means that the curvature is high or we have a low effective mass. We generally think of flat bands as having high effective mass due to small orbital overlap. This gives them a high density of states because all of the states have to be in a smaller, narrow band. At least near the bottom or top of our band, this description will be consistent with the equation we derive for the free electron density of states dependent on effective mass. Again, narrow bands with a high effective mass will have a large density of states. We can now understand band diagrams of semiconductors, particularly ones that have their band gaps at the k=0 point or gamma point. For example, in gallium arsenide, the S and P valence states of both gallium and arsenic hybridized into sp3 hybrids, where on average there was only one electron for each state. These states combined into bonding and antibonding molecular orbitals, where the bonding molecular orbital was completely filled and the antibonding orbital completely empty. These 4 bonding molecular orbitals become the 4 valence bands that are completely filled below the band gap. There's one S-like band that runs up from k=0, and one light valence band which has a large dispersion running down from the gamma point or k=0. There are also 2 flatter bands which we call the heavy hole valence bands. In the direction from k=0 or gamma to the L point or the X point in the Brillouin zone, they are exactly degenerate and drawn as a single line. Above the band gap, we will find the empty conduction band states made from the antibonding molecular orbitals containing both S and p-type character. Zinc selenide has the same tetrahedrally bonded structure as gallium arsenide, but the zinc and selenium states are further apart in energy. This results in a larger gap between the bonding and antibonding molecular orbitals, which results in a larger band gap between the conduction band and the valence band. Also, the larger difference between the atomic states between zinc and selenium results in a slightly weaker bonding or overlap between the neighboring orbitals. This results in a slight flattening of the bands, leading to higher density of states and higher effective masses for zinc selenide. We see now why the dispersion relation of our filled valence bands will have a local maximum often at k equals 0. The free charge carriers that are responsible for electrical conduction in the valence band can be thought of as the missing electrons or holes in the valence band, which rise to the top of the valence band like bubbles. Although it is really the opposite electron in the valence band that is conducting the charge, it is easier to follow and count the number of holes in the valence band. Because the curvature of the valence band is downward, the second derivative of energy with respect to k is negative. This would normally give us a negative effective mass. For holes, though, the convention is not to think of the effective mass as negative, but to invert our E versus K diagram to retain a parabolic dispersion relation. In this way, we have a positive effective mass for holes, still depending on the second derivative of the dispersion relation. By inverting our E versus K diagram for holes, we think of our holes as reducing their energy by rising to the top of the band. The convention for holes is to think of their electric charge as plus E, while that of electrons is minus E. In gallium arsenide, the valence band maximum is at the same K vector as the conduction band minimum, giving us what we call a direct band gap. This makes for efficient photon absorption and emission, as photons have no crystal momentum. Silicon, on the other hand, has its valence band maximum at the k equals 0 or gamma point, but its conduction band minimum is away from k equals 0 at another point in the first Brion zone. This leads to an indirect band gap because the conduction band minimum is not directly above the valence band maximum. The process for moving an electron between the conduction band minimum and the valence band maximum is slower in an indirect semiconductor because it is more complicated. A phonon or lattice vibration is usually required for conservation of crystal momentum before a photon can be used to release or absorb the energy.